Now, this course deals with fractal geometry, a discipline of mathematics that has developed over the last say about 20 years, and it has found a lot of applications in various disciplines of science and engineering, and that is why it has attracted much attention and also imagination of adventurous students. Now, so this course we will try to cover in a span of a few lectures. The basic idea is that of geometry. Now, what does geometry deal with? Geometry deals with objects and spaces. This is something that is often missed in regular geometry lectures, that geometry deals with objects and spaces. Points, lines, spheres, rectangular parallelepipeds, these things are objects and they live in spaces. For example, a zero-dimensional point can lie on a one-dimensional line or a two-dimensional plane. So, a point which is a zero-dimensional object can lie on say a line, in which case we will say that a zero-dimensional object is lying on a one-dimensional space, or it can lie on a two-dimensional space. Likewise, a line can live in a two-dimensional space, or a curve can live in a three-dimensional space. In other words, what I am trying to convey is that there are two types of objects that are of interest in geometry: the objects and the spaces, and the objects live in spaces. And when we talk about objects living in spaces, we always find that they live in spaces of dimension either greater than or equal to the dimension of the objects. Now, for much of the human history, people have studied only regular objects, idealized objects, like a sphere, like a triangle, like a rectangular parallelepiped, things that we really never come across in our daily life. Spheres, triangles, obviously these are idealization from what we actually have in daily life, and this is sort of a legacy of Pythagoras and Euclid. They devised the concept of idealizing what we see in actual reality in nature, idealizing, studying the property of those idealized objects, and thereby we have a whole lot of Euclidean geometry which deals with such idealized objects. Only over the in the matter of spaces, these are objects. In the matter of spaces also, we were talking about either a flat sheet of paper for a 2D space, or a 3D space with a flat characteristics. Flat characteristics means mathematically it means that if we have 2 points, their minimum distance is governed by the Pythagoras law. So, you have the idealized objects and the idealized space. Now, by the end of the 19th century, there was a revolution in mathematics, especially in geometry, through the work of Riemann, Gauss, Lobachevsky, people like that, we sort of learned that there could be other types of spaces, curved spaces, positively curved space, negatively curved space, and those things. And Einstein found a very profound application of that in the theory of gravitation. But objects still remained the ideal ones. We still talked about triangles, or one of the classical things by which we illustrate the difference between a curved space and a flat space is the angle between in a triangle. So, if you have a triangle drawn in a flat piece of paper, the angles contained will be 180 degrees, while if you have a football or the surface of an earth, and if you try to draw a triangle over that, the angles contained will be larger than 180 degrees. So, that was a difference between the two types of geometries, the flat geometry, flat space, and the curved space. But the object still remained a triangle, an idealized object. And only over the last say 20 years or so, we are breaking out of the narrow confines of the idealized Euclidean objects. Now, science is beginning to recognize that the things that we really see in nature, things that are far from idealized, things that are crooked, things that are curved, bent, and they do not look like the things that we study in school geometry textbooks. Those things are actually valid subjects of study in geometry, and fractal geometry is essentially concerning that. What we really see around us, the things around us, their geometry, their specific properties, that is what fractal geometry is all about. So, having laid this ground, let me come to the point that what exactly is the difference between the things that we see in nature and the things that we study in our school textbooks, the objects. One of the things one of the aspects that often, if you think of it, it will immediately catch your attention is that the non-idealized things, or if you have a ideal curve given by some kind of a function y is equal to f of x. This is an idealized object given by some kind of a function. Now, if I ask you what is the difference between this object and the kind of curves that you see in nature, one thing immediately will come to your attention, that if you now look at a very small range of this, then it almost resembles a straight line, right. Take any idealized curve like the circle, the parabola, like whatever curve you can think of. If you look at smaller and smaller portions of that curve, it will always flatten into a straight line. And in fact, that is how the derivative is defined, right, because the derivative is nothing but dy dx is nothing but limit of delta x tending to 0 delta y delta x. So, what we do, we have this term, this part as delta x and this term as delta y. So, we vary x by a weeny bit and we observe the variation, resulting variation in the variable y. We have this delta x by delta y by delta x, and we take a limit tending to 0, and that is what we call dy dx, the derivative of y with respect to f x at this point. Now, if this be the definition, obviously it rests on the assumption that as you bring this one closer, as this one comes closer, it actually approximates a straight line, and this straight line slope is this fellow. So, there has to be the straight line existing, but there lies the main distinction between an idealized curve and the actual curves that we see in nature. What the main difference is that the actual curves that you see in nature are not differentiable anywhere. meaning that you come closer, this slope continuously keeps changing. It is not differentiable. It's this particular thing does not exist as a unique number. So, that is the main distinction between an idealized curve and the curve that we come across in nature. The ones that we come across in nature are continuous, but non-differentiable geometrical objects. Let us give some examples for such curves in nature. For example, for the electrical engineers, it will be easy to visualize on a power station. If you continuously keep a record of the load on a power station, then you will get some kind of a graph, right? Some kind of a graph all the time. There will be some, but there will be variations all the time, because somewhere somebody is always switching on and off some power. It's varying, and that variation, if you zoom on in a very small scale, you will find that this term does not exist, meaning that it is a non-differentiable curve. Similarly is the situation with the recordings of the oscillations during earthquakes. If you have that as the curve, that as the geometrical object, and if you zoom closer, you will find that it does not smoothen into straight line, and thereby this term does not exist. And so you see that there are existing curves in nature which does not follow this property that the derivative will exist. In fact, there are curves. In fact, most curves are such that they are continuous, but there is no derivative. The next major distinction can be illustrated through the person who invented this fractal geometry. His name is Benoit Mandelbrot. This man asked by now a famous question. He said, can we measure the length of the coastline of England? How long is the coastline of England? Well, if you think, it appears that okay, we can always measure. We will go around it and we will measure. But the moment you start to ponder on this question, you will realize the amount that we will measure depends on the yardstick of measurement. Imagine the coastline may be something like this, the island of England, very badly drawn, but nevertheless it is. So, if you have the yardstick of measurement say this long, then you will start from here, you will make one section here, then a section there, then a section there, then a section there, and as a result you will miss whatever happened in between. So, you might say okay, let us reduce it, but so long as you had this yardstick of measurement, if you go on cutting this boundary and you simply add them up, you will get some number. You might argue that okay, reduce it, fine, reduce it. So, you come to this part, and so on and so forth. As a result, you still miss some creeks and crevices. As you go on further reducing it, you see more and more creeks and bends, and finally when you make it 1 centimeter long, still you see bends around pebbles in the seashore. And if you continue this argument, and at every stage you find that the length that you are measuring going on increasing. The more you are decreasing the yardstick length, the more the total measured perimeter of the island is going up. And as a result, by continuing this logic, it is not difficult to realize that as the length, the yardstick of measurement that goes to 0, the measured length of the coastline goes to infinity, a startling result. This implies that the coastline of England, or any island for that matter, is a geometrical object of infinite length, yet enclosing a finite area. That is important. So, the conclusion is most natural curves are of infinite length yet enclosing so that is the property of curves. What is the similar property of say surfaces? Take a natural surface, for example, our lungs. What is the purpose of the lungs? The purpose is to absorb as much oxygen as possible from the air. As a result, the requirement is that it should have the maximum surface area exposed to air. Yet it must have a finite volume, a small possible volume, because it has to be accommodated within the rib cage, and that immediately leads to the conclusion that the surface of the lung must be of the same character, that it is a surface of infinite volume yet enclosing a finite infinite area yet enclosing a finite volume. So, you see, these are the aspects in which the natural objects, natural geometrical objects differ from the idealized ones. They are continuous but non-differentiable. But this kind of objects then obviously need a different kind of characterization. The way we learn to characterize, the way we learn to understand geometrical objects, the same type of understanding will not work, because we have to deal with non-idealized objects. As Mandelbrot once said, that mountains are not cones, clouds are not spheres, lightnings are not straight lines. Obviously, the way we understood those idealized objects like cones, triangles, straight lines, those things will not work when we try to actually understand the nature of geometrical objects that we find in nature. So, we need a different formalism, we need a different technique, and for that comes the question of dimension. What is dimension? It is rather strange that we never come across the actual meaning, sense of the term dimension in school or college textbooks. Our idea of dimension is often based on common sense. I mean, we sort of intuitively understand what dimension is. Like a point is a zero dimensional object, a line is a one dimensional object, a surface is a two dimensional object. This kind of sort of intuitive understanding we have, and naturally our understanding is that the dimension is an integer, and we have considerable difficulty in imagining anything otherwise. Well, let me tell you that the ancient people had the same kind of difficulty when they had to imagine that there could be numbers that are not natural numbers. The natural numbers came naturally to them, like 2 men, 25 bananas, 6 children. These are natural numbers. But when man faced the problem of measuring, say, length, area, time, it was necessary to conceive fractions. That's what they did, and that is how the narrow confines of the natural numbers was broken. Men broke free of a sort of limitation in concept. It seems that now it is time for us to break free of the concept of the integer dimensions. Why? It must first be understood that the concept of dimension of an object and the dimension of the embedding space are two different things. This is something we often do not understand, and as a result we mess up the concept of the dimension of an object and the dimension of a embedding space. What is the dimension of embedding space? That is essentially given by the degrees of freedom. If you have if you have a say one dimensional space, this means that you have freedom in moving left and right. That is the concept of a one dimensional object, one dimensional space. If you have a two dimensional space, it means that you have freedom of moving left, right as well as front, back. If you have a three dimensional space, you can move left, right, you can move front, back as well as up, down. So you have 3 degrees of freedom. So the dimension of the embedding space is related to the degrees of freedom. Naturally, since degrees of freedom are integers, therefore the dimension of the embedding space must be an integer. But that does not mean the dimension of the object also must be integer, because the object lives in the space and its dimension must be understood by the way it fills space, and that is not a priori given. That would be the same as the dimension of the embedding space. Let us illustrate how. What is the actual concept of the dimension of an object? The dimension of an object is, as I told you, essentially depends on how it fills space, how it fills space. So in order to illustrate what it means, how it fills space, or what actually we understand by the word dimension of an object, let us take a square as an example. So we have a square. Fine. So this square as an object is living in the two dimensional space, and we are trying to probe how does it fill the space. So what we will have to do is to divide the embedding space, the space on which it lives, into sort of boxes. We will have to divide this space into boxes, and that we can easily do by placing a graph paper on it. Okay. So we simply place a graph paper on it, as a result of which we have essentially divided into boxes. So now we have to count, we have to find out how many of these elements, these are the boxes, these are the boxes, can you see? Yes. So we have divided the embedding space into the boxes, and we have to answer the question, how does this fellow fill space? Essentially that means that how many of these boxes are necessary in order to cover this object. So we can see that in this particular case we need 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, and thereby we have 64 of these boxes. Now if I subdivide the space by a smaller box size, for example, let these be my boxes, smaller ones. Okay. So each of the boxes that we considered earlier, now let us divide into 4 boxes. Probably you can see, right? This is one box, that is one box, that is one box, that is one box, and so on and so forth. So how many boxes will be necessary now? In this direction, earlier there were 8 boxes, now there will be twice the number of that, which means 16 boxes. In this side also it will be 16 boxes. So you have 16 square. So this essentially means that okay, in the next step you can further bring down the size of the boxes. It will naturally go up, the number of boxes that will be necessary to cover it. And how it will go up is that if the side of the box side length, if that is epsilon, and n number of boxes, then we have the relation n, which is a function of epsilon, is 1 by epsilon square, right? That is what we saw when it was this big, it required 64. When it was its side was half the size, then we required 16 times 16, and even smaller, it will go up simply this way. Can you see that? Yes. So it will go up as 1 by epsilon square. So this is where the number 2 appears. You might ask that, okay, you have taken a very simple object. What if you take not this object but something slightly different, say for example a triangle. So we take a triangle. Okay, so fine. So we join them, we have a triangle. Now this triangle, if you take this triangle as the object that we want to investigate, and we place the same graph paper on that, then how will the number, what will be the number of boxes that you need to cover it? You notice that initially you need a larger number. You need this box because a part of the box is covered, is necessary in order to cover this object. Therefore, this box fully has to be counted. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 and all that. So you can easily count, but since it is not very well drawn triangle, I needed to have a scale, but you can easily understand that you will get a number that is more than half the number that you needed earlier, more than that. Now if you further subdivide the boxes, then you would see it will slowly approach whatever was necessary earlier. It will approach half that number, but it will approach, not that it will immediately be that number. So initially you need all these full boxes. Later you need only this box and this box, and this box will go out, this box and this box and this box will go out, and so on and so forth. So if as you keep on subdividing, you will find that you are closely approximating this hypotenuse, and as a result your number n, so this was for the square. For the triangle, this was for the square. For the triangle, what happens? N of epsilon will tend to, I cannot say that it is exactly that, because we have seen that it will tend to half 1 by epsilon square. You might ask, what if we take, say, a circle? I am drawing by hand, but I could have drawn by some more finer means. And if we cover, can we argue what will be it will converge to this number? As you keep on reducing the box size, each box size, then it will slowly converge onto for the circle, n epsilon will converge onto pi by 4 1 by epsilon square. So notice these things. This was for the square, this was for the triangle, and this was for the circle. And we know all these are idealized geometrical objects. So as yet we have not gone into the territory of non-idealized objects, but we are trying to extract what do we understand by the dimension of the object. So once we have this, we can sort of in a general way we can write we will keep this one for a future reference, but in general we can write some k into 1 by epsilon square. So it converges to, it is not equal to, it converges to. So So far we had here k is equal to 1, here k is equal to half, here k is equal to pi by 4. In general, for all these objects we can in general write k. And then we ask the question, how can we extract the number 2 from this? We can go the following way, simple school day algebra. We take the logarithm of both sides, ln n epsilon is equal to, I am considering the situation after it has already tended to, that is why I am using the notation of equal to. So, this is ln k plus 2 will come forward, 2 ln 1 by epsilon, right. Now, we are trying to extract this number 2. So, we write it as, we take it in the left hand side, we say the 2 equal to, we have ln n of epsilon divided by ln 1 by epsilon minus ln k divided by ln 1 by epsilon, right. So, this is the number 2. Now, we were seeking this number 2 because that we knew represents the dimension of those objects. We had considered the square, we had considered the triangle, the circle. We know that these are 2-dimensional objects. So, we are trying to extract the number 2. So, as epsilon tends to 0, what will happen to this one? This denominator, this term, the second term will tend to what? The second term will vanish, because this term will go up. So, the second term will go to 0. We cannot say the same thing about this term. So, we essentially conclude that the dimension of any object, in this case it was 2, but in general the dimension d is nothing but ln n of epsilon divided by ln 1 by epsilon. Okay. Now, this is important. We have the rule that the dimension is actually understood by means of this. So, what did we do actually? We took any object, we subdivided the embedding space into equal number of covering boxes, something that will completely cover the embedding space, and then we counted the number of boxes that are necessary to cover that object. After we have counted, we reduce the box size epsilon, and thereby we as we go towards epsilon tending to 0, if we keep on measuring this, then this should give me the dimension of the object. Clear? So, for these objects, initially if you start measuring, it will not be 2, but it will converge onto the number 2. But nevertheless, it will converge. If you really do it, you will find that you will get something like this, that if you vary the epsilon and if you vary if you plot the dimension measured this way, then for any object, say for a parabola, if you take a parabola and if you do the same procedure, it will start from another value and it will converge onto the number 1. If you take a triangle or a sphere, then it will start from some value and it will converge onto the number 2. So, ultimately, as you reduce the epsilon, what matters is where does this number converge. So, that is the dimension. So, that is our concept of dimension. And finally, if you apply this method to any geometrical object, the objects that are found in nature, if you apply this method, wherever it converges, that will be the dimension. If this is the concept of dimension, this is the idea of dimension, that we have to find out how many boxes of the embedding space are necessary to cover it, and we reduce the box size to 0 progressively and find out this number, and wherever that number converges, that is the concept of dimension. Then obviously for any non idealized objects we have to follow the same procedure. Let us illustrate how to do that. This is a non ideal geometrical object, right. Just before coming to the class, I had picked it up from one of the plants in our garden, and so this is a natural object which every one of you have seen. So we, in order to measure the dimension, we cover the embedding space by means of the equal number of boxes, and then we start counting. So how will we count? The number of boxes that are necessary in order to cover this object. So 1, 2, 3, 4, 5, 6, 7, 8, but not this, these were not necessary, 9, 10, 11, so on and so forth. If we count and if we then put it here, take the logarithm, and for every stage of counting, each stage of counting means each box size that you have taken. In this case it is 1 centimeter box size, then if you take that in place of the epsilon, then you will get a number. Reduce the box size to half a centimeter, and then you again do the counting, and then you again put it in these two places, the half a centimeter here and the number of boxes that was covered here. So what we generally do is to find out how many of these are necessary. That means we have a total size, and then we say that my box size is 1/10 that size, 1/20 that size, 100 that size, so that the epsilon is also a non-dimensional number. We do not call it in terms of centimeters. So epsilon is a non-dimensional distance, that is in terms of the size of the total, and if you go on doing this exercise for every iteration, for every stage of this counting, that means in every stage we have set a particular side length. In the initial, you might say I have divided the whole into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that kind of 12 divisions, so 12 by 12 square. In the next stage we make it half of that, and so on and so forth. If you do it that way, then you will find that always converges onto a number that is not integer, between 1 and 2, something that has a fractional value. So all geometrical objects that are obtained from nature yield this kind of the similarity of all geometrical objects is that if you repeat this procedure, if you carry this procedure for any geometrical objects, you will always find a number that is non-integer. Now it is time to clearly state what is a fractal. Fractals are geometrical objects with fractional dimension. Fractals are geometrical objects with fractional dimension. It is important, so let me write it. The definition of a fractal: well, if it is made up of points over a line, spread over a line, a point is of dimension 0, a line is of dimension 1. So if I have a set of points spread over the line, then if I do this procedure, its dimension will come between 0 and 1. If I have a embedding space of a sheet of paper and we have got some kind of a curved line, and we measure its dimension this way, then its dimension will come somewhere between 1 and 2. If you have a surface a rather crooked surface embedded in a 3D space, then if we measure its dimension, it will come between 2 and 3 and so on and so forth. So, the actual dimension of the object will be less than the dimension of the embedding space. It will always happen. Only in idealized objects, say a cube embedded in a 3D space. A cube means if it is idealized cube, not made by a carpenter. If it is made by carpenter, the surface has always some non-idealities. So, I am talking about an idealized cube. Then the object's dimension will be equal to the embedding space's dimension. Else it will always be less, and unless it is a idealized, say, circle embedded in a 3D space, in which case the circle's dimension, as I already shown, it will turn out to be, it will converge onto the number 2. That is why its dimension will be said to be 2. But if that object is a non-idealized object, its that particular curve will always converge onto a number that is not 2. So, this is the concept of fractal geometry. The way to obtain that number, fractal dimension, is that clear? All that we do is, if we have any object, we simply put that object, we embed it by the space, and we count the number. Accordingly, we write this equation, we put it in this equation, and we get the value d. Nowadays, with the advent of the computers, this procedure has become significantly simple, because all we need to do is to take a photograph of that, make it into a file that is a binary file. Binary file means these points where the pixels that contain this object will be 1 and the rest of the space will be 0. And then simply by means of a computer, we can do this procedure of embedding by means of different size boxes and counting how many of these boxes are necessary to cover this object. Ultimately, the maximum extent to which you will be able to reduce epsilon is the pixel size. So, we cannot really, even in idea, we cannot really in actual practice, even if we do it by a computer, we cannot really bring it down to 0. We can bring it down to the maximum extent of the pixel size. But when we do so, when we draw the curve, actually, it will come to a point and then we have to stop, and then we have to extrapolate it to cross that. So, where it crosses, that is the number that we are seeking. Clear? So, this is a procedure then that you should yourself be able to do. There are hundreds of images available on the net. You can also take pictures. Many of you have digital cameras. Simply you have to make it as a binary image, 0 and 1, and then you have to count. What use is this number? After all these procedures, you have got a number, fine, but what use is this number? That is the important aspect. After all, this number signifies the way it differs from the idealized ones, and the way it differs from the idealized ones would be the way it is more crooked, curved, twisted. So, the ones that we generally ignore when we idealize things, the things that we had ignored, the dimension or the amount by which the dimension differs from a integer dimension, that will indicate that character, how crooked it is, how bent it is, how twisted it is. So, that is what it will measure. Looking at an object, we do have a intuitive feeling, how crooked it is, how bent it is, how twisted it is, how non-ideal it is. We have a feeling like that, but this allows us to get a quantitative estimate of that. Okay. So far so good, we have obtained a quantitative estimate. What do we do with it? Well, just think of the situations where that character matters. For example, in the rivers, silt particles flow. Why does it flow? Because it floats in the water, and then it gets carried by the flow of the stream. Which particles will flow and which particles will settle in the bottom as silt particles? That obviously depends on the specific gravity of the individual particles, the size of the individual particles and stuff like that. Of course, that will. But given the same value of these, the specific gravity being the same, the sizes being the same, what will determine whether a particular particle will be carried by the stream or it will settle? It will depend on its surface properties. The more crooked the surface, the more probability it has to be carried with the stream. So, here the surface properties would matter. Automobile exhausts give out fumes, right? You can see in the crowded Indian cities, you see the fumes as black soot coming out of the exhaust pipe, and you heard that causes harm to our breathing ducts. Out of those, there are various particles of various sizes, shapes, and the crookedness of the surface. And obviously, the more crooked the surface, the more probability it has to attach to the breathing ducts and cause harm. So, here also you see that the character of the surface matters. When there is a switch, normal electrical switch, you press the switch and two metal make contact. Do every point of the two metal pieces make contact? No, obviously not. Because if you look at the surface by means of a electron microscope, you will see that there are so much imperfection that they look like mountains. And there are two things which both have this kind of imperfections, and obviously the ones that make contact are simply the places where they touch each other. And obviously the character of the contact will depend on how crooked are the surfaces. There again the surface character matters. The situation with say solid electrolytes, where when you are say using some kind of a electrolyte and electrodes, there is the electrolyte which say dilute solution of hydrochloric acid, and you have put some electrodes to generate hydrogen or oxygen. Really the reactions take place on the surfaces of the electrodes. So, the surface, how crooked are the surface, what is the surface property, the generation of hydrogen oxygen will depend on that. Similarly, when you talk about the solid catalysts, for example, there is a reaction in which gases are taking part in the reaction and there is some solid catalyst. How efficient will be the catalyst not only depends on its property, its chemical properties and stuff like that, but also depends on the surface, the amount of surface that is exposed to the reactants. So, all these cases, it is easy to see that the fractal dimension will matter. In geology, there is a large body of knowledge in which you see when the rocks were formed, they are formed in some process, and there are big rocks, small rocks, pebbles, sand, grains, and the geologists often cut the rocks to see what is inside. You see structures within structures, structures within structures, and all these structures now geologists are trying to relate to the way they formed. So, the geometry of those very irregularly shaped structures actually have some meaning. So, you see in various disciplines we have specific use of this concept of the fractal dimension. uh, the economics data set for the exchange rates, the one that you find in newspaper every day, that today the dollar rupee exchange rate was so much, tomorrow it is so much. If you go to any of those banks, you will find it is changing hour by hour. There is a computer which keeps giving the hourly record of that. Now, if you go to the places where actual exchanges are taking place, you will find that it changes minute by minute. So, you see, that is again a data set that has complexities within complexities. Similar is the situation of the Sensex, the any economic index. These things are all curves that are fractal in nature, in the sense that you cannot differentiate them. If you want to measure the fractal dimension, you get a number that is between 1 and 2. So, today we will end with the idea that fractal geometry is a new type of geometry that tries to represent actual natural objects. The main distinctions are: one, that the main natural objects are geometrical objects that are continuous but not differentiable anywhere. Secondly, they are continuous surfaces, yet infinite surfaces, yet enclosing finite volumes. Thirdly, most importantly, they have a fractional dimension. So, we will end with this today. We will continue in the next class.